When I first studied linear algebra, I always thought of the row echelon form as the end result of Gaussian elimination. But the thing is, textbooks say something different. A matrix is in row echelon form if all zero rows are at the bottom and all pivots are to the right of higher pivots. The thing is, why? How on earth is this equivalent to a matrix being an end result of Gaussian elimination? Are these really the same, and where does this definition actually come from? Maybe I should be a bit more specific. What do I actually mean by end result of Gaussian elimination? If you have a matrix A and you transform it to a row echelon form U, then how do we describe this U? It's clearly the end result of the Gaussian elimination, but what's interesting, I realized, is if you do Gaussian elimination on this matrix U itself, again, the algorithm has nothing left to do. Each pivot is already in position and every entry below the pivots is already zero. The algorithm has done its work. If you do it again, it doesn't do anything. So I'm going to say that a matrix is the end result of a Gaussian elimination if and only if it is unchanged when you do Gaussian elimination on it. In this video, we are going to prove rigorously, at least somewhat rigorously, that invariance under Gaussian elimination, meaning a matrix not changing when you do the algorithm on it, is equivalent to saying that it has these two properties. I've always wanted to know, why are these two actually equivalent? So let's do it. Firstly, we need to prove this direction. We'll prove that if a matrix doesn't change under Gaussian elimination, it has these two properties. Now, the way we're going to do this is actually using the contrapositive. You have a zero row not at the bottom, or you have a pivot to the left of a higher pivot, and this would imply that a change occurs under Gaussian elimination. We're going to prove these two things separately. First, we're going to prove the zero row property, that if a matrix is invariant under Gaussian elimination, all zero rows are at the bottom. Or by the contrapositive, if we have a zero row followed by a non-zero row, then Gaussian elimination will correct this. It will change it. That's what we're going to try to prove firstly. And the way we're going to do it is using induction. Yes, we're going to induct on n, keeping m fixed. This is going to be pretty crazy. For the base case, we have an m by 1 matrix, which is just a vector in Rm, and it has m rows and, well, 1 column. And we have a zero row followed by a non-zero row. So I'm assuming P here is non-zero. Okay, so in one case, let's say P is the first non-zero entry, we'd need to show that Gaussian elimination will change this. Well, if you look back at the algorithm, it chooses a pivot and swaps the pivot with row 1. So the first pivot this will choose, if P is the first non-zero entry, would just be P. And we'll swap P to the top with a row operation. But swapping is going to change the matrix, right? So there we go, we're done in that case at least. The matrix does change if you have this sort of structure. Now, what if P is not the first non-zero entry? Well, then a different pivot, which is above, will be chosen. And if you go back to the algorithm, we use row operations to eliminate entries below the pivot. So P will be eliminated using row operations, and that is a change. P is going to become 0. So we've proven that in both cases, this sort of structure results in a change under Gaussian elimination, and we've proven it for the base case. Now the inductive hypothesis. I should have mentioned we're actually doing strong induction. So we're going to suppose that for a particular n, this sort of structure where you have a zero row and then a non-zero row will change after Gaussian elimination. And we're assuming this for matrices m by c, for c all the way up to n. This is a pretty strong statement, and this is going to help us. Now we need to prove for m by n plus 1 matrices. So suppose we have something like this, where there's m rows and n plus 1 column. And I'm going to call this matrix A, okay? That's usually the letter we use for matrices. So we have a zero row here, and after it is a non-zero row, because P is non-zero, we'll assume at least. Okay, now we need to do Gaussian elimination on this. So it goes left to right, Gaussian elimination, so maybe we consider this left submatrix here. I'll call this submatrix B. Now, in one case, imagine if Gaussian elimination changes the matrix B when you just do it on B. Well, in that case, we're actually done, because doing the algorithm on A, well, the start of that part will be doing the algorithm on B, because Gaussian elimination goes left to right. So if it changes B, it will also change A. And in that case, we're done. We've proven that Gaussian elimination changes this. But this is a trivial case, right? We're more interested in a difficult case where B doesn't change under Gaussian elimination. Now what? Well, we can actually use the inductive hypothesis. This is basically saying if you have a zero row and then a non-zero row, then Gaussian elimination changes that matrix. By contrapositive, it means if the matrix doesn't change, then you actually don't have an instance of a 0 row and then a non-zero row. So we can actually apply that here because B doesn't change under Gaussian elimination. And the number of columns in B is actually at most n, because there's n plus 1 columns in A, and we define B to be the matrix to the left of that column containing P. So in the worst case, it's going to have n columns, so B satisfies the inductive hypothesis. So what do we know then? We know that B doesn't have this instance of a 0 row followed by a non-zero row. So it actually must mean, because we have a 0 row here, everything after it is also 0. So all of these entries here, we can just say safely that these are 0. Okay, now what? Well, we need to do Gaussian elimination on this matrix and prove that there's going to be a change. So how do you continue the algorithm? Well, if you go back, step 3 involves repeating on a submatrix. So we really need to think, where is the rightmost pivot in B? And once we get that, we can repeat the algorithm by looking at the submatrix to the bottom right of that pivot. So we'll suppose it's here. Now, because it's a pivot, it's the first non-zero entry of that row. So that means everything to the left is 0. Now, also, I want to focus on this part here. This also is a submatrix of A, and it has at most n columns, and it's also invariant under the algorithm because it's part of B, and B is invariant under the algorithm by our assumption. So we can use the inductive hypothesis again, and that means if you have a 0 row, after it is also 0 rows. So these guys are 0. Now looking at this part, if there was a non-zero element here, it would have to be eliminated by Gaussian elimination because you eliminate entries below the pivot. Remember, that's part of the algorithm. So that wouldn't work because B is invariant. So it must be these guys are all 0. Now looking at these, if you have even one non-zero element here, then, well, you'll have a pivot in that row. That's the case because on the left you have all zeros, as we've just shown. So if you have a non-zero element here, we have a pivot. Why is that a problem? Because Q is the rightmost pivot of B. So after it, there are no more pivots. So that would be a contradiction. These guys have to be 0. Okay, now we've figured that out. Let's try to continue the algorithm past B. And the way we do it is by considering this submatrix, ignoring the gray values. We need to do Gaussian elimination on this because it's a recursive algorithm. So you look for the first non-zero column, which wouldn't be these because these are all 0 as we've shown. It would be this. And we try to find the first pivot. Now, this is actually similar to the base case. We kind of shown that if you have this sort of structure, remember, there's going to be a change in Gaussian elimination. Either P becomes the pivot and it's swapped upwards, or P is itself eliminated. Either way, the matrix is going to change. So therefore, we've actually proven it. We've proven that the matrix will change under Gaussian elimination if you have this sort of structure. And we actually did need the strong induction. So yeah, by strong induction, if you have a 0 row followed by a non-zero row, Gaussian elimination will cause a change, and this is for any size matrix. But by contrapositive, it means if the algorithm doesn't cause a change, then you have no instance of this 0 row followed by a non-zero row. In other words, all 0 rows are at the bottom. And this is the first part of our theorem proved. Now we have to look at the pivot property. Trust me, this one isn't as bad, okay? So we need to prove that if you have a matrix which doesn't change, then all pivots are to the right of higher pivots. By contrapositive, if we have an instance where a pivot is to the left of some higher pivot, Gaussian elimination will correct that basically. So let's look at an example. Well, this is an arbitrary example, okay? Suppose Q and P are non-zero. Well, here we have Q as a pivot, and it's to the left of the higher pivot, which is P. So this is what we're considering. We just need to show Gaussian elimination will change this matrix. So consider this submatrix. We can argue similarly. If this changes under elimination, then obviously we're done. But then that's the easy case. We need to consider if it doesn't change under Gaussian elimination, then what do we do? So that's what we'll assume. Suppose this yellow matrix is invariant under Gaussian elimination. But the thing is, we already know something about such matrices. We actually know from the theorem we just proved that all 0 rows are at the bottom. So if we have a 0 row here, everything below it is also 0. So everything in this box is 0, okay? Just keep that in mind. Now we need to think where is the rightmost pivot of this yellow matrix, because Gaussian elimination will continue past that point. Well, it can't be anywhere down here. It has to be somewhere up here. So suppose the entry is Q. Q is a pivot. So that means everything to the left of it in that row is 0. And we can argue similarly that these guys are 0 and this is 0 and this is 0. We did this in the previous result. Okay, now we continue the algorithm past this point, looking at, well, this submatrix, where you ignore the gray stuff. Now all of this is 0, so the first non-zero column, which Gaussian elimination will consider, is this. And we can basically use the base case again if you really want to for that previous result. This is definitely going to change under Gaussian elimination. Either Q will become the pivot or it will be eliminated. So we've proven it. The pivot property is done. If a pivot is to the left of a higher pivot, the Gaussian elimination will correct that. Okay, so we've proven now by contrapositive stuff, if Gaussian elimination doesn't change a matrix, it has these two properties. But now we want to show the reverse direction because that will truly mean that these are equivalent. So suppose we have a non-zero matrix which does have the two properties, and I'm saying non-zero because it's kind of trivial. Gaussian elimination will not change a zero matrix. Okay, now what? Well, maybe it looks something like this. Suppose the first few columns are all 0, and then you have one non-zero column here with P and Q, where P and Q are non-zero. But is this possible? I'm wondering, is it actually possible to have two non-zero elements in a column? Well, obviously not, because then Q is a pivot, P is also a pivot, and Q is not to the right of the higher pivot P. It's actually just below it. So that violates this second condition, right? So actually we can't have two non-zero elements in this column. We can only have one. So I'll just remove Q. Everything in this column is 0, okay, except P. Keep that in mind. We can actually show that P has to be at the top of this column. If it's not at the top, then this top entry is 0, and then there's going to be a pivot for the first row somewhere over here, but then P is to the left of that higher pivot, which also contradicts the second condition. So that won't work. Instead, P has to be at the top. If we do the first two steps of Gaussian elimination on this matrix, we look for the first non-zero column, and then find it and swap a pivot to the top. But we don't need to swap a pivot, it's already at the top. P is at the top. And we eliminate below the pivot, but that also doesn't need to be done because everything below P is 0. So these first two steps of the algorithm actually don't change the matrix. This is really important. The next step is about the submatrix, which you usually remove the pivot row and column, but actually there's a way to do it just by removing the row. It's actually equivalent, because you're just going to be left with a bunch of 0 columns on the left which don't really affect anything. So we can actually remove the first row and that suffices. Now we have another submatrix. Now think about it. Does this submatrix have the same properties as A? Well, clearly all the 0 rows would still be at the bottom, but also all pivots are still to the right of higher pivots. Removing the first row just removes a pivot from the top. It doesn't change the ordering of pivots below, right? So this submatrix has the same two properties as A. By the same logic, the first two steps of the algorithm on this submatrix will not change it either. And then the next step is repeating on the next submatrix, which is this one. And we can just repeat this logic. The algorithm will not change this matrix, at least the first two steps. And then we can repeat and so on and so forth until the matrix is, well, we're done with it. We could have done this with induction, but I think we've done enough induction today. If you have these two properties, the algorithm actually doesn't change the matrix. So we've proven the other implication, therefore these are equivalent. A matrix not changing as a result of the algorithm is equivalent to saying it has these two properties. So now if we use the row echelon form definition that most textbooks use, this is the row echelon form theorem. A matrix is invariant under the algorithm if and only if it is in row echelon form. Thanks for watching, and I hope you now know why the row echelon form is actually defined how it is and why it's equivalent to the intuitive understanding of it. I also realized while editing the video I said Gaussian elimination a stupid number of times. Okay, thanks for watching.